Next, we're going to look at some more alkene addition reactions, and we're going to learn the products and reactants and their step-by-step mechanisms. So the first one that we're going to look at is a hydration reaction. And hydration means the addition of water. And so when we add water to an alkene, so in our equation, our example below, we have ethylene, and we're adding water in the presence of a strong acid that's acting as a catalyst. So you might recall from general chemistry that a catalyst is something that helps speed up the rate of a reaction without itself being consumed. So essentially it gets regenerated in a later step. So this reaction goes a lot faster if you use an acid catalyst, such as sulfuric acid or perchloric acid or nitric acid. Those are all sources of hydrogen ion because they're strong acids. And so our product that we produce from this hydration reaction is that we make an alcohol. So the two things that we added across the double bond were hydrogen and a hydroxyl group, which that functional group is equal to the alcohol. Now notice on the equation on the left-hand side, we started with ethylene as an example, which ethylene is symmetrical. Both of the carbons have two hydrogens coming off. But this reaction is regioselective. And so if we look at the equation on the right-hand side now, we have an alkene that is unsymmetrical. So just like when we talked about our first mechanism, we had to decide what side the hydrogen would go to and what side the hydroxyl group would go to. So notice that the hydroxyl group actually ends up on the most substituted side. And so then the hydrogen ends up on the least substituted side, only we don't see that hydrogen being added because we don't show them on the line bond structure. But really that hydrogen would be coming off right there, the one that was added. Next, we're going to go through the mechanism for hydration reaction. When you look at the arrow and you're starting with some alkene, you might see on the arrow one of two things. You might see H plus or H3O plus with water written, or you might just see someone write H plus or H3O plus without the water. Either way you see it written, you want to recognize that a strong acid, which is abbreviated using hydrogen ion or hydronium ion, both of these are strong acids, those are already aqueous. Strong acids are in water. They're not pure strong acid. Even the most concentrated strong acid you could buy when you purchase it is already an aqueous acid. So it's just assumed that that is in water already. So if you were to see over the arrow someone write H2SO4 versus H3O plus or just H plus, those are all the same thing. Those are all representing an acid catalyzed hydration reaction. So there's a lot of ways in organic chemistry to write the same thing. And that's kind of what's hard in the beginning, is getting enough experience to be able to identify the subtle differences, but realize that it is the same mechanism. So starting off, when we have our nucleophilic attack, what we attack first is a proton of our acid. And it's perfectly okay to use the structure of H3O plus instead of, for example, drawing out the full structure of nitric acid or sulfuric acid. Commonly, when we're just talking about a strong acid, we draw H3O plus instead. So in this reaction, we have H3O plus, strong acid, acting as a catalyst in water. We're doing a hydration reaction. So our alkene, the pi electrons, act as a nucleophile. So nucleophiles are going to be electron rich. They're going to donate their electrons to an electrophilic center or to a proton. So if they're attacking an electrophilic center, we call it a nucleophile. If they're attacking a proton, we call it a base. But it really means the same thing. So in this case, our base or nucleophile, our alkene, will attack the proton of the acid. The electrons will stay with the oxygen. Notice that oxygen had a positive formal charge, and when it picks up that extra set of electrons from this covalent bond right here, then what will happen is it'll be neutral. So essentially, we lose water in that step, or we form water, either way. So sometimes you'll see where they'll write minus H2O under the arrow to show that we formed water by abstracting that first proton. So now when we grab that proton off of the hydronium ion, we have to decide, is the proton going to go on the least substituted side, or is the proton going to end up on the most substituted side? Because notice we started with an unsymmetrical alkene. So we saw on the equation on the previous slide that the proton ended up on the least substituted side, and the hydroxyl group ended up on the most substituted side. So we're going to add our proton to the least substituted side, and then what we're left with on the most substituted side is essentially a carbon that now doesn't have 4 bonds to it because that double bond broke. So we have a carbocation that's formed on the most substituted side. And remember from our hydrohalogenation reaction that this carbocation intermediate went through the more stable intermediate. So in this case, we have a tertiary carbocation. And since it's tertiary, it's more stable than the potential secondary carbocation being formed if the carbocation was on the least substituted side. That's why that one doesn't get formed. So now that we have our tertiary carbocation, we can have attack of a nucleophile to that electrophilic center. And so what could function as a nucleophile in this reaction? Well, we just made some water, and it is a hydration reaction. So we're going to draw our Lewis structure of water. So 2 lone pairs on the oxygen, no formal charges. That's what we formed when we removed the proton from our acid, plus there's some already swimming around because the acid's aqueous. A lone pair of electrons will function as a nucleophile, and it will attack our electrophilic carbon, our carbocation. So remember, your arrows always start where the electrons are. So they start at the nucleophiles or the bases where it's electron rich, and they point towards, they head towards where the electrons are going. So in this case, they're going towards the carbocation. And so then we're now going to have a new bond that forms there. So here's still our hydrogen hanging out that we added from step 1. Here is the new bond that we just formed in between carbon and oxygen. Carbon is no longer a carbocation. It now has 4 valence electrons. It has a complete octet. But oxygen, notice it has that bonding pattern of 3 bonds, and it has an unwritten lone pair on there. So that oxygen, you should recognize, has a +1 formal charge. And so we want to essentially, throughout our mechanisms, alleviate these formal charges. They're not particularly stable. So how can we get rid of a formal charge on oxygen? We can remove a proton in an acid-base reaction step. So water, we learned, is amphoteric. So that means it can function as an acid or a base, depending upon who it's reacting with. In this case, the water is going to function as a base and abstract an acidic proton from this oxonium ion. So this oxonium ion, notice it's really similar to the hydronium ion, except for one of the hydrogens is now this alkyl group coming off. But we can, it's essentially acidic, and we can remove one of the acidic protons. So our oxygen, with its lone pair of electrons on water, will grab a proton. The electrons in the covalent bond will go to oxygen when that proton gets ripped off. And that will end up generating the neutral hydroxyl group. So our hydroxyl group, we're left with a lone pair of electrons there from the covalent bond. We had a lone pair of electrons on there, and now we have just 1 hydrogen on there. So no more formal charge because oxygen's divalent, has 2 bonds and 2 lone pairs. So it's neutral. And notice our oxygen is on the most substituted side where the alkene was most substituted, and the hydrogen is on the least substituted side. So this is our alcohol product. And in this case, if we're going to classify it, this is our alpha carbon. We have 1, 2, 3 carbons coming off our alpha carbon. So this is a tertiary alcohol. You could start with a variety of alkenes. This generic alkene that I used in the beginning that I pretty much start all the examples with is just some generic unsymmetrical alkene that I picked. But you're going to see that when you start doing reactions and looking at products and reactants that you could have a multitude of alkenes. So you have to really look and understand where you're going to be adding your groups across. And you have to understand step by step the arrow pushing and the mechanism that's taking place. I also want to point out that the product that we're interested in, the product that you really have to show, the major product, is this tertiary alcohol. So this tertiary alcohol is what you would draw if you were just drawing products and reactants. This would be the product of this reaction. Now, what did we also form? When our water in the previous step, right here, grabbed that proton off of the oxonium ion, it formed what? It formed hydronium ion. So we reformed H3O plus in that final step. So hydronium ion is a catalyst. And so a catalyst is essentially regenerated, not consumed in a chemical reaction, and it helps speed it up. It helps speed it up by protonating the alkene and creating the carbocation rather than having direct nucleophilic attack of the water to the double bond, which would be a lot slower. So it created a better or a more powerful electrophile by creating the carbocation for us, essentially. But you wouldn't actually have to show this hydronium ion in your products, just the primary major product that we're interested in. Next, we're going to look at a reaction called the halogenation reaction. And a halogenation reaction starts with an alkene and it reacts it with a halogen. In this example, we're going to look at using bromine, which is Br2, but you could modify this mechanism and turn it into a chlorination using Cl2. The steps would be the same, only we would substitute our initial bromine for chlorine. So both of those are divalent halogens. So the mechanism would follow step by step. So just know that if you see those practice problems or homework, that the halogen can be substituted, but we're just going to be using bromine for our examples. The reaction proceeds through an intermediate, called the bromonium ion intermediate. What will happen is the bromide ion will attack the more substituted carbon of that bromonium ion intermediate and open it up. It's a kind of a ring structure. It'll attack the site of the most positive charge and give us a dibromo product. So we're going to end up with two bromo groups added across the double bond. So we really don't have to think about what side yet is more substituted and yet when we're more substituted and less substituted when we're just looking at products and reactants. But when we're looking at the mechanism, we're going to have to think about that. So products and reactants, that just comes from the equation. So if we look at our equation, our chemical equation, we start with an alkene. In this case, the alkene is in a ring, and that's helpful because we can see some stereochemistry after easily with a ring, even though we haven't covered full stereochemistry just yet. And our reactant, the one that I care about, is this Br2. Don't worry about the denominator of the arrow. That is CCl4, which is carbon tetrachloride. That is just a solvent. You don't have to write that under there. But the reaction does have to be carried out in some sort of solvent system. So often solvents will be placed below the arrow. You guys did this reaction in lab and you did not use carbon tetrachloride as your solvent because it's a rather dangerous solvent. So just write over the arrow the Br2 and we'll be good. Now notice our products here. So when we added the bromine across the double bond, of course the double bond ends up breaking. Those pi electrons will attack the Br2 and we'll see how in a second. But we're using wedges and dashes to indicate if we had syn addition or anti-addition. So here we have a bromine pointed down. That's what's used to represent the wedge there. It's showing that it's going down from the plane of the ring. And then that's the dash. So the dash is down. And then on this one, we have the wedge, which that wedge is representing that it's pointed up. But regardless of what one's wedge and what one's dash, notice that they're opposite. One is wedge and one is dash. So what that tells us is that the bromines are added to opposite faces of the ring. They're not both down or they're not both up. So what this is called is anti-stereochemistry. where they are added to opposite faces there. So when we go through our mechanism, we'll see why that occurs. Why don't we get syn stereochemistry or syn addition, and they don't end up on the same face? So when you draw your products, you don't have to use wedges and dashes if you're not using a ring, but you should show one bromine pointed up and the other one pointed down using the correct geometry. Let's go through the halogenation mechanism. So in this case, we're doing a bromination. But remember, you could also do a chlorination. If you use Cl2 instead. So we're using Br2 for our example. So over the arrow, you would just see written Br2. Maybe in some textbooks, you will see a solvent down here, but don't worry about that solvent part. So just like we saw before, we're going to have a nucleophilic attack starting with our alkene. Now, you might be wondering, well, what's the electrophile? Isn't bromine really electronegative? And it is, it's electronegative, but it's also nonpolar. So we normally would say that this molecule does not have a partial positive and a partial negative. We would just assume that the electrons are equally shared. Since it's nonpolar, all it has is London dispersion forces present. But even in a nonpolar molecule, remember, they can develop a dipole moment. They can develop an instantaneous dipole, which can then lead to an induced dipole in neighboring molecules. So remember, the electrons are not staying still. They are moving. And bromine, that's not shown here, but there's 1, 2, 3 lone pairs on each bromine. They have a complete octet. And those electrons are moving. So at any one moment, let's say that the electrons that are contained within the covalent bond shift towards the right bromine. They shift, and so that would cause this bromine to be partially negative, and it would cause the other bromine to be partially positive. This is exactly what happens with molecules that only experience London dispersion forces. This is how they have their properties, is due to the shifting of those electrons. And the more electrons something has, the stronger its London dispersion forces, the more opportunities for those electrons to move around. So even a nonpolar molecule overall can develop an instantaneous dipole just from the movement of those electrons. So now we can see where our pi electrons of our alkene are going to attack. But the attack is going to be a little different than what we saw before, because and we know this is true because of the anti-addition that is seen, and we don't get any syn addition. So what happens is the alkene, the nucleophilic alkene pi electrons attack the partial positive bromine, and then one of the lone pairs of electrons on the bromine immediately goes back and attacks a carbocation that would be forming. So we would be forming a carbocation. Actually, we would be forming that partial charge over there. I'm going to erase that because that's not something you want to leave there. But just like we saw last time, we had a full carbocation. Well, one would be starting to form, but as soon as it starts to form, that same bromine that got attacked by the pi electrons goes back and attacks that carbocation that would be formed. So let's actually show it like this. The pi electrons from this side attacking bromine, and then these electrons going back and attacking where that carbocation would be. So what this forms is something called the bromonium ion intermediate. And if you used chlorine, it would be a chlorinium ion intermediate. So we have this 3-membered ring, and our bromine has a positive formal charge. So that's where this plus is coming from. Your bromine has 1, 2, so 2, 4, 6 electrons around it, so it has a +1 formal charge there. And notice the carbon doesn't have a positive formal charge because it does have 8 valence electrons around it. It has a full octet. So we do have still in this example more substituted side, and we do have a least substituted side. So now for our next step after we form the bromonium ion intermediate, it's pretty bulky. The bromonium ion intermediate is planar. It's just got 3 members to it, and our incoming nucleophile could either attack on the most substituted side or the least substituted side. And we have to decide, is it going to come and attack right here, or is it going to come and attack right there? And if you think back to the analysis we just did on the previous example, we attacked the side that had the most substituted, the more alkyl groups coming off, because that was the site where it was, the stable positive charge. It's true here as well. Even though we don't have a full carbocation, we're going to attack where that positive carbocation will be. That is still the site of the positive charge, because all three of these atoms within this bromonium ion intermediate, the two carbons and the bromine, since they're in a ring, they are all sharing that positive charge together. So in this case, we would attack the more substituted carbon side. So we're going to leave that green arrow there. Our bromide got formed from when we formed the bromonium ion intermediate. This covalent bond actually broke. So that covalent bond broke between the two bromines in our initial reactant, and those electrons will stay with it. So that's where we have this bromide ion floating around from. It got formed after that initial first step. So this can function as a nucleophile. It's going to attack the site of where the positive charge would be, which is the most substituted side of the alkene. And then it breaks open the bromonium ion intermediate. So after it attacks that carbon, this covalent bond right here snaps open, and those electrons stay with the bromine, and that gets rid of the positive charge there. So we form a new bond to the more substituted side right here on this carbon. That is what we just added, our nucleophilic bromide that came in. And then when that ring breaks open, we end up with a bromo group on the least substituted side as well. That's still there from the bromonium ion intermediate. And when it attacks, we say it goes through something called anti-attack. And this has to do with the steric hindrance of that bulky, rather large bromonium ion. So it attacks the bromide, the nucleophile, attacks from the opposite side or the opposite face that the bromonium ion is on. It does not attack from the same side. So let me draw this on here and we'll get rid of it after, but it would not come around and squeeze in right there and attack on the same face as the bromonium ion intermediate, because it's just too crowded and sterically hindered. So that would lead to syn addition. And we don't see that, so we know that the mechanism follows anti-attack, where it attacks from the opposite face of that intermediate. And so that's why we end up with one of these pointed up and one of these pointed down. They're on opposite faces, so anti-addition. Next, we're going to cover some reactions that are derivatives of the halogenation reaction that we just went through. So either using bromine or using chlorine as our halogen. Now we're going to introduce a competing nucleophile. So look at the name of this reaction. It's called Halohydrin. So halo is for halogen. Hydrin, or hydration, we said was for water. So our competing nucleophile in this reaction is going to be water. We're going to still go through a bromonium ion intermediate if we're using bromine. But what's going to happen is the water is going to be present in a larger amount than the bromide ion. So in that second step, instead of bromide coming in and is attacking as a nucleophile, we're going to see water come in and attack as a nucleophile. So we're going to create a mixed product. This is going to be a halohydrin. We're going to have an alcohol on one side and an alkyl halide that we added to the other. So what you're going to see, how this is written, is you're going to have Br2 on the top of the arrow, and some books will throw water up there as well, but water can also be written at the bottom because it can be used as a solvent that acts as a competing nucleophile as well. So later in the semester, we will dive into solvents very deeply and see how choosing your solvent is a super important aspect of running any organic reaction, because they can help, they can interfere, they can do all kinds of things. But right now, think of the water as a solvent, but also a competing nucleophile. It's part of the reaction. So you might also see the reaction just written like this, Br2 / H2O. So they're both attacking. Sometimes solvents are not involved in the reaction, and we don't even include them, as you saw with the CCl4, the carbon tetrachloride. There are solvents for pretty much every reaction you do, but sometimes people just don't include them above or below the arrow. But we are going to be using the water in our mechanism, so we will include that. The halohydrin reaction is regioselective. So we're going to start here with an unsymmetrical alkene, and we have our most substituted side at carbon 1 and our least substituted side at carbon 2. So let's just look at what our reactants and products are. When we do the reaction with bromine in a solvent like water, a competing nucleophile, what we end up with is a hydroxyl group added, and notice the hydroxyl group is on the most substituted side. And on the other side, we ended up with our halogen. We started with Br2, so we added a bromo group. And the bromo group ended up on the least substituted side. And that's a result of this reaction still going through that bromonium ion intermediate. Also notice, did we have anti-addition or did we have syn addition? The hydroxyl group is on a dash, so think of the dash as representing down for now. And the bromo group is on a wedge, and think of the wedge as pointed up. So we have one down and one up. So that would represent anti-addition or anti-stereochemistry, where they are on opposite faces. All right, so our reaction, we're going to go through the mechanism in a second, and it's going to be very similar to what we just saw for our halogenation reaction, but now we're having that additional competing nucleophile come in, which is going to be the water. You're going to see that some of these mechanisms start to seem the same, and that's because I'm trying to get you to recognize the patterns. And so the more patterns that you can recognize, the less memorization you have to do. So just think about them like practicing when the reaction is very similar, but just has a little bit of a change in one step, such as this one will have. So pretty much these first few steps are going to be exactly what we just talked about previously. So we started with our Br2, and we saw that one side developed a partial positive charge, one side developed a partial negative charge due to the shifting of those electrons. And our alkene acted as a nucleophile, and it attacked a bromine. And when it did, a lone pair of electrons on that same bromine went back and attacked the carbocation that would be forming, which gave us that three-membered bromonium ion. And the covalent bond between the two bromines broke, because bromine is not going to have that many bonds to it. It would have a much higher charge. And then the electrons go to the they go to the bromine and form bromide ion. So that step, when that covalent bond breaks right here, this is where your bromide ion comes from. So now we lose our pi electrons, but we form a bromonium ion intermediate. We got the bond here that was formed to bromine and the bond here that was formed to bromine. Notice the bromonium ion intermediate is directly on where the double bond was. We have a positive formal charge, and that's kind of shared among the two carbons and the bromine. And it's a planar, bulky, large intermediate. So we never attack from the same face as the bromonium ion intermediate. We always attack from opposite faces due to the steric hindrance. So that's anti-attack. So instead of having that bromide ion come in and attack, because it's not present in as high of a concentration as the solvent, the water can be a competing nucleophile and come in and attack. So lone pair of electrons on oxygen will attack the more substituted side, because that's the more stable site that has the most positive charge there. And we're going to break open that bromonium ion. So these electrons in between carbon and bromine on that more substituted side, it has to break open because carbon can't have more than 4 bonds. So those electrons go to the bromine. So our bromine has those electrons there that were from that bond breaking open. And this bond is still attached to the bromo group. That's on the least substituted side where the halogen ends up staying. And on our more substituted side, right here, we have a new bond from carbon on the more substituted side to the oxygen. And that is our oxonium ion. It's acidic, just like hydronium ion would be. So our oxygen has a positive formal charge. We have to deprotonate in order to get rid of that formal charge. And so we're going to use something that could function as a nucleophile or essentially a base to remove a proton in this next step. And we could use our bromide ion, or technically we could even use water. Either one would pretty much show the same thing. We're going to deprotonate. So we form bromide in step one, but we also have water floating around as well. Bromide is going to come along and grab that proton right there. It's going to form HBr. That's kind of a side product that would form, so we can say minus HBr under the arrow. And when it grabs that proton, the electrons right here between oxygen and hydrogen will stay with the oxygen. And so what we're left with is our oxygen has 2 lone pairs on it, 2 single bonds, divalent. We have a hydroxyl group that got added, which that's our alcohol. And we ended up with a bromo group, our halogen, on the least substituted side. So the alcohol goes to the more substituted side, the halogen ends up on the least substituted side. That's a result of that bromonium ion being formed after step 1, and then how it gets opened up in step 2. So it's never the other way around. And notice one is being shown pointed up and the other is being shown pointed down. So we have the anti-stereochemistry. There is also a halohydrin ether analog reaction, which is essentially the same mechanism that we just saw, only instead of having water as a competing nucleophile, we're instead going to have an alcohol solvent as a competing nucleophile. So we end up with a haloether product instead. So when we had water, we ended up with an alcohol. And when we start with an alcohol as our solvent, we end up with an ether. So we're still going to start with the halogens such as chlorine, Cl2, or bromine, Br2. Our competing nucleophile will be an alcohol. We'll still go through the bromonium ion intermediate. The alcohol is more abundant. It's essentially the solvent that the reaction is carried out in, so there's much more of it. We're going to have the alcohol attacking the bromonium ion and opening that structure up. And we're going to end up producing an ether and an alkyl halide. So here's 2 examples. We're starting with an unsymmetrical alkene. So you could see this written as steps 1, 2, or you could see it written as we saw before, just Br2 slash, and then notice it says ROH. The R represents, you don't want to write it like this in real life when you guys are doing your homework or your quizzes or your exams. You don't write R, you write what it actually is. ROH is just a generic alcohol. So it could be in real life MEOH or ETOH or PROH. We haven't named alcohols just yet, but this would be, for example, methanol. This would be ethanol. This would be propanol. So the R gets changed out for what it really is, a methyl group, an ethyl group, a propyl group. You don't want to leave it just as a generic R group when you're actually doing real questions and answering real problems on exams, for example. But when we look at this, we have our halogen, which could be bromine or chlorine, whatever, and we're going to end up with, on our more substituted side, the ether. So you see how that R group is actually showing up on the product. In real life, that could be something like MEO, or it could be ETO. It's not going to be R in real life, but we're just keeping it simple and using an R group to represent any alkyl group. So don't make the mistake of leaving that. And on the least substituted side, we end up with our halogen. So just like we saw before with our alcohol and our halogen. If we look at a ring structure, we can also see that it's regioselective. So on our more substituted side, where our ether is produced, that one is pointed up. In this example, it's on the wedge. And on our least substituted side, where our halogen went, it's on a dash, so that is down. So this is anti-stereochemistry once again. And all of these are because they're all going through that same bromonium ion intermediate. So because of that being bulky and large and being attacked from the opposite face, we always end up with one group that opens it up on the opposite face as the bromo group or the chloro group that was making up that bulky three-membered intermediate. So this is where understanding the mechanism comes into play. There's a lot less to memorize if you understand step by step how a reaction works. Okay, so we're going to go through the Haloether mechanism. This should look really familiar to you. We have our nucleophile, which is our alkene. We're going to start with our Br2. So on your arrow, Br2/ROH. Remember, ROH is just any alcohol. The R will actually change depending upon what alcohol the problem is actually using. But for now, it just says R because we're keeping it generic. So starting off, our alkene attacks the bromine. A lone pair of electrons on one of the bromines goes back and attacks where the carbocation will be forming, giving us the bromonium ion intermediate. The covalent bond breaks. The electrons go with bromine to form a bromide ion that leaves. We end up with our three-membered bromonium ion intermediate. There's a positive formal charge. The more substituted side is the site of the most positive charge that will be attacked through anti-attack, opposite face, of our competing nucleophile. Our competing nucleophile in this case is an alcohol, so ROH. It's the oxygen that does the attacking because oxygen is electronegative more than carbon or hydrogen is. So just like with water, we still start with the alcohol. The alcohol will attack from the opposite face, the more substituted side, and break open the bromonium ion intermediate. So we have a new bond here between our more substituted carbon and the oxygen of the alcohol, and our halogen is bonded to the least substituted side. Our oxygen has a positive formal charge on it because it has 3 bonds and 1 lone pair of electrons. To get rid of our positive formal charge, we use our bromide ion that was formed in step 1. One of the lone pairs of electrons can come over and attack the hydrogen ion and grab that. And so the electrons in between there will stay with the oxygen. So our oxygen ends up with the electrons sitting on it that were in between that covalent bond where the proton got grabbed off. We formed some HBr, some hydrobromic acid, as a side product when the bromide abstracted a proton. We're left with an ROH, which is an ether group. R would change depending upon what the identity of the alcohol was. And on our least substituted side, we have our halogen. So this mechanism is exactly like the halohydrin that we just saw, only instead of having an alcohol, we have an ether. But it's still on the most substituted side because of how that bromonium ion was broken open. And just to point out, if you started with Cl2, you would have this. You would have a chloro group there instead of a bromo group because you would have a chloronium ion intermediate. And so the mechanism is exactly the same. We've just been using Br2 in our example. But you could substitute what your initial halogen is. We can also produce a mixed alkyl halide where we end up with 2 different halogen groups on our product. So in this case, if we start with a halogen such as Br2, but we run it in the presence of a competing nucleophile, we saw a couple different competing nucleophiles already. We saw water, we saw alcohol. Well, now we're going to use a different halide ion. We're going to use the chloride ion. The chloride ion is more electronegative than the bromide ion, and so what will happen is the chloride ion will open up the bromonium ion intermediate as long as it's used in a separate step. So we want to use that chloride ion after we form our bromonium ion intermediate. It'll attack the site of the most positive charge and we'll end up with a mixed alkyl halide. This reaction is also regioselective. So we're going to go through that same anti-attack that we've seen several times now. So let's look at these two equations for this reaction, the products and reactants. We have our alkene, it's unsymmetrical. Here's our most substituted side. Here's our least substituted side. Notice in step 1, we're using Br2. In step 2, we're using NaCl. The sodium is just a cation, and it's essentially a spectator. It's not participating in the reaction. It's paired up with chloride initially because it's an ionic salt. What we're interested in is the competing nucleophile, which will be the chloride, the anion portion of that salt. So what we form then is we have a chloro group that is on the more substituted side. So that competing nucleophile always ended up on the most substituted side. And we have a bromo group that ended up on the least substituted side. And that's what we've seen for the last few reactions there. And so if we look at a ring, we can see the regioselectivity of this reaction better. We have our more substituted side with a methyl group coming off, our least substituted side. The chloro group here is on a wedge, and that is face up. The bromo group is on the least substituted side, and it's on a dash, so that's face down. So these two are opposite faces, so they went through that anti-attack. They have anti-stereochemistry. So you're always going to see that bromo group, and if you're using Br2 as the initial halogen, ends up on the least substituted side. And in this case, the chloro group ends up on the most substituted side. But they're on opposite faces, one up and one down, due to how that bromonium ion had to open up. It had to open up from anti-attack. Okay, so hopefully by now this mechanism is getting boring because you've seen it so much. So on your arrow, you might also see this written as Br2/NaCl. That's another way that people will write it, even though we're essentially using this in step 1 and this in step 2. So our alkene attacks one of our bromides. It becomes polarized due to the shifting of those electrons. An electron pair goes back and attacks the carbocation that would be. The covalent bond breaks. The electrons stay with the other bromine and form a bromide ion. So we do see a bromide ion formed still in that first step. The accumulation of those 3 arrows gives us our bromonium ion intermediate. Now, normally in that very first mechanism we did when we did halogenation, we took a bromide ion that was formed from step 1 and we attacked the site of the most positive charge. Well, now the point is we have a competing nucleophile, and that is the chloride, not the sodium. So our chloride is more electronegative than the bromide is. So the chloride comes and attacks, anti-attack, attacks the more substituted carbon, which is the site of the positive charge. Even though it's shared amongst all 3 of them, that's the most positive charge site. And it breaks open the bromonium ion intermediate. And so we form our mixed alkyl halide. We have our chloride attached to the most substituted side. We have our bromo attached to the least substituted side. And it went through that anti-attack due to the steric hindrance of the bromonium ion. So all 3 of the last mechanisms were similar. We had water as a competing nucleophile, an alcohol, and in this case, a chloride ion. All 3 were competing nucleophiles. All the competing nucleophiles always ended up on the more substituted side. The thing that we started with, which in all of our examples was Br2, left us with a bromo group on the least substituted side. So that is due to the formation of that bromonium ion intermediate. You also want to understand that in the final product, one is pointed up, one is pointed down. And if you were showing that with a ring, you can show that easily by using wedges and dashes. Don't use wedges and dashes yet when you're drawing on non-ring structures because there is a whole set of rules to learn for using those, and we'll cover those in the stereochemistry chapter. So for now, we're just showing using lines, one up, one down, to show that they are anti stereochemistry. They're on opposite faces to one another in the final product.